Right, Year 12. This is probably the most important of all of the electricity sections because it is, as the title says, how to actually solve any questions involving circuits. Now this will also be true next year when we do capacitors or magnetic circuits. It's all about the same thing. So, questions can come in one of two forms. They might ask you to start with some knowledge about some components, so back to our last section, so you need to know a little bit there. But mainly we can treat everything in the circuits as either types of voltages, currents, or resistances. Okay, and they all fall into those groups. So the link is, of course, Ohm's law. So how do we go about it? Well, it all comes up with two fundamental rules, and these were discovered by a guy called Kirchhoff, who perhaps facetiously we've called Captain Obvious, because these are the things that you have been doing for a long time. They are very, very obvious. Okay? However, they are fundamental to what's going on. So, what are they? Well, the two laws are about the two things that you can measure in a circuit. So it's either about measuring the currents or it's measuring the potential differences in the circuit. Okay, and we can use these to work out equations for resistance, but we don't have to. Okay, we could actually do a lot of the work thinking about the current, where is it flowing, and the different voltages, and we can measure the voltage out, the voltages left at different places, the potential difference. So when we look at that, we're going to actually kind of work around these two principles. Now, I'm not going to give you the real rules because they're a little bit more complicated and they don't seem to make sense sometimes. Let me just adjust this because it's clicking around. There we go, that should lock it. So the first one is basically saying wherever you are in a circuit, the algebraic sum of the current is zero, which means that the current flowing in is the same as the current flowing out of any point in the circuit. Charge is conserved. If it's electrons, then the electrons going somewhere have to come out at the other end. And that's the crucial bit, is conservation of charge. So in this diagram, we're going to take somewhere obvious where you might want to think about this, which is at a junction. So when you get to a junction, the current flowing in will be the same as all of the current flowing out. Notice that it's the sum of. So here, on the other side, we're going to have three currents flowing in, so the total of those is what equals the current flowing out. Not all circuits look this simple. So the rule is always true, but it can be used. The more complex the circuit, the more important it is to use the rule. So in this diagram, the current 1 flowing out of the cell, which I'm going to call the total current most of the time because that's the one that matters, the one that's coming out of the cell, gets to the junction and then it splits three ways, and all of those currents will always be all of the little blue people running around with their bags of energy. So they come in, there's a split in the corridor, there are different ways for it to flow. Okay, so what we can say is electrons have to go everywhere. Let's be more general. Charge carriers, which, as I say, most of the time is electrons. So I'm just going to put electrons question mark. Doesn't have to be. Have to be conserved. Now, obviously, chemical reactions can happen in a cell, but anywhere in the circuit, once it's left the cell, between that electrode and that electrode, all the current must add up. Okay, so what is the current for? Current is your SI unit because without the current, nothing else can work. So everything's based on where this current flows. But the role of the current is this idea of the loop rule, which is to think about where does the energy go in. It's all about conservation of energy. Okay, so this was conservation of charge up here. The crucial bit is this is where it gets a little bit difficult because it depends on the type of circuit. So we have a series circuit, we have a parallel circuit, but the rule has to still work. It still has to be productive for all. So in the top one it's more obvious, and the crucial bit is we have to consider a single loop. Okay, a loop that has an EMF and PDs in it. So in other words, it's got to go through a cell or a battery, in which case you add up the EMF of each cell to make your battery. There may be more than one source of energy, but again, you're just adding them up. So what that means is the energy in our EMF has to go somewhere. So it's either going to go here, or here, or here, or maybe it's lost inside the cell itself. So there's some internal resistance, so we get a voltage drop, a potential difference within the cell as well. Okay, so in this diagram, EMF, there's only one of them, equals V1 plus V2 plus V3. Oh, excuse me, plus V4, because there's 4 resistors. Now the crucial bit is, notice the symbolism. EMF is E, or epsilon rather, and PDs are always signified with V. So when we say V equals IR, we're talking about the PDs. Alright? Now, in this second circuit, it looks more complicated, but if we think back to the idea of a single loop with an EMF in, then effectively we have one loop that runs round like that, okay, and a second loop that runs round like that. Okay, so that's loop 1 and that's loop 2. If we follow the charges that come out of the cell and go all the way down to this bottom bulb in loop 2, then they will lose their energy, they will produce a voltage and go back to the cell for more. They are not flowing around here, so this is not a loop. It has to go through a cell and then the rest of the circuit, so a single loop in a circuit. So what we've got going on is the same energy as it flows around. So in this case, each charge, I'll put that in speech marks, each charge loses its energy at any resistance, okay, V equals IR. So just keep going back to that, but it loses at any resistance that it flows through. Okay, so that's the crucial bit. It has to flow through it to lose the energy, to have the energy stolen from it. Now you might want to think of this as we are going to draw our circuits running from the top to the bottom. So electronic engineers do this quite commonly. We put the cell or the energy source, it could be a generator, whatever, but we will tend to talk about the top of your circuit being at the high voltage. The bottom we tend to say is at 0 volts. It doesn't actually have to be at 0 volts as long as there's 9 between them in this version. But if you connect it to earth, then it will be at 0 volts. Okay, so that will ensure 0 PD at that point. Okay, now in terms of this, again, maybe useful to think about height, and some people think of this in 3 dimensions, but the key point is as the charges flow, they drop through different resistances, and as they drop through your resistance, they'll give out some of their energy, so that by the bottom they've got none left. Okay, they've returned the root back. And obviously do have a little bit of kinetic energy, but so there is a little bit of voltage drop along the wires, but nothing compared to the resistances you put in. So basically we're approximating by saying all the voltage is here. Okay, but if you study that, it could be any resistance it flows through, including your wiring. Now, if there are multiple loops, then again, as the electrons fall down through them, fall down the energy levels through them, then they will lose that energy. Okay, they will give out that energy to the resistances. And that's why in a parallel circuit, if it's just parallel, each PD is the same as the energy it was given in the first place. So the PDs across each of these is equal to the voltage of the cell, the EMF. Whereas here, they're going to add up because they have to go through all of them before they've lost all their energy. So you can think of it kind of like slides or falls through, just like we did the ladders approach. Okay, and we take the model a little bit further. We talk about, you know, numbers of people and so on. Obviously, it's not 100 people on these slides. It's millions and millions and millions of billions of them, if we're talking about your average current. PD gives a little bit of detail as well. So my model, a different model there, but very commonly falling down from the top is very, very common. Now, in lesson I would have got you to do this, but if, and this is a big question, if you need circuit resistance, okay, then you can work that out using those two Kirchhoff's rules. But often you're just using the two Kirchhoff's rules to get your answer. Kirchhoff, whatever. So, if you were to find out, if you just needed to know resistors together, series, parallel, whatever, then what we can do is use Kirchhoff's to work it out. So I'm going to use the second law, because for that, that's the law about PDs. Okay, why? Because we're going to lose a bit of PD at each one, so they add up, which is nice and convenient. So if I take my epsilon, okay, in this case, epsilon equals V1 plus V2 plus V3. All of the potential difference, all of the energy is lost as it goes along. I've got 3 ammeters here just to kind of break this up, but I know that you know, obviously current just flows around and around. Assuming these are all perfect meters, assuming no current flows around through the voltmeters. So in a perfect setup, which is how it works, if we took away all the meters, this would still be happening. You just wouldn't be able to see the readings on a scale anyway. Okay, so if we were to replace these, what I can say is that I can have the first current flowing through the first resistor will give me my first PD, plus I2 flowing through R2, plus I3 flowing through R3. Okay, so those will be the PDs. Okay, but now I've introduced current, so I'm starting to think about resistance, because the current through the resistance is what causes our PD. Okay, so effectively, I'm going to say the circuit resistance, okay, and I'm going to change that to total circuit resistance, is the EMF divided by current. Okay, so what I need to do is get rid of these currents to work it out. So what I'm going to do is cheat ever so slightly, rearrange that and put this in here. So we're going to have IR total equals I R1 plus R2 plus I R3, and I can do that because of course all of these values of current and the total current is the same as, by Kirchhoff's first law, I equals I1 equals I2 equals I3. Okay, and so if I get that, then what we've got is very simply RT, or it simplifies because I can delete all the way through, divide all the way through, it equals just the sum of the resistances. Okay, so we've just simply proved that we can add up the resistance. Why? Because it all depends on where they leave the energy and where they're travelling, where the charges flow through. So Kirchhoff's two laws. Now in a parallel circuit, it's slightly more complicated because they have a choice of ways to go. Not that they choose, but they are forced down. So if we use Kirchhoff's first law, we know that the I, I'll just put it in here, flowing out of our current is I1 plus I2 plus I3. Okay, because they have that choice. So they're all going to add up to my original current flowing from the cell. Now, again, if we want to think about resistance, then we need to get R into here instead. So I'm going to use the same Ohm's law. Okay, so I'll just put in but I equals V over R. Okay, so in my total, using the same idea, I'm going to have epsilon for my input voltage, and I'm just using that vaguest sense because that's a PD, but it's the energy in, so energy in divided by my total resistance is going to equal, again, same idea, voltage 1 flowing through resistance 1 plus voltage 2 through resistance 2 plus voltage 3, or PD3 over resistance 3, which of course gives us current 3. So each of those gives the current, but Kirchhoff strikes again. Second law, we know that E equals V1 equals V2 equals V3 in this parallel circuit. We know that the drop is the same, and so what that means is 1 over total resistance equals 1 over R1 plus 1 over1 over R2 plus 1 over R3. So that's our generic way of finding resistances if they're nicely in a series or parallel circuit. So both of these nice and fairly straightforward. This one people do get wrong, so what I'm actually going to do is change that. Instead of writing 1 over RT, because people always forget to find the inverse at the end of it, I'm going to make it total resistance and put the rest of it in brackets. However many resistances you have in parallel, with a -1, and that is far more useful. So if you do this as a habit, when you put it to the power of -1, people always then find the reciprocal, but they don't if you write it like this. So use this way of doing it. Just remind you that in the data book it will say this, but use this, remember this. It's nice and straightforward, it makes it much easier. So we can use these, but often in multiple choice questions more than anywhere else, because you tend to be given readings in the circuit rather than all of the values. Okay, so let's have a bit of a look at a question here. Okay, so if I go into the workbook, and in the lesson I got you to do 14 and 15, but we can work through this one to check the whole thing through. So as I said in the lesson, make sure you're writing down values when you've got them. Okay, so we have a lot going on here. We haven't got any values of current, so we're going to have to use, or voltage really, so we're going to have to use resistance. So I'm going to put in, that's 30 ohms, because I can simply add that in my head. And then what I'm going to do is have to deal with these together as a lump. Okay, why have I put those two together? Let's have a look at that. So the current that flows from A to B in the top half of the loop has to flow through both. So it's seeing, shall we say, if your electrons could see, it would see both those at the same time. So you've simplified it now to 3 resistances, 1, 2 and 3, because we've changed those two into a single one. Again, using the same idea, as the electrons come along, as they get to B, or if you prefer going from the other end, it doesn't matter too much. But as they get there, they're going to see that there is a choice. So it sees both of those choices at the same time. So your next step is to put those two together. So I'm going to call this resistance AB, between A and B. Okay, and I'm going to put that as 1 over 30 plus 1 over 15 to the minus 1. Okay. Now what that will equal is, do it in fractions if you can, it makes it easier. So that's 2/30ths. So it's going to equal 3/30ths to the minus 1 equals 30 over 3, 10 ohms. Okay, so does that figure? It's less than 15, the smallest one. So yes, all of this is now 10 ohms. Okay, so I'm going to just kind of join that on so I can see that. So I'm going to go for my total resistance in my circuit is 10 followed by 10. 10 plus 10 equals 20 ohms. Okay, again, note I'm showing my steps so I can see what's going on. So now I have the whole circuit. I'm going to underline that because that's really quite useful. I've got the whole circuit resistance, I've got the whole EMF, voltage coming from the cell. So I know the current in the circuit, V over R, let's call it that. So I've got 30 divided by 20. Now if you're thinking, should I put EMF? Well, the PD will also add up to 30 because the energy that comes out of the circuit is the energy that goes in. So I'm not too worried if you put V or E here. Most people, the vast majority in the country, will use that, including engineers. So that equals 1.5 amps, and as I said, what I'm going to do is I'm going to label that on 1.5 amps. Okay, coming out of the cell, etc. Now, straight away, I can see the voltage across these. Why? Because I know that the PD here plus the PD here will add up to 30. And I know, I can do this thoroughly, which I will do here, but I know that because that's 10 and that's all 10, it's going to get the same amount each. So I know that's 15 volts. And I'm going to put the V as well because it's easy to get mixed up. So 15 volts across the lot. Can we check that? Well, yes, I can. I know that, let's call it the V of the 10 ohm resistor equals IR. So that's going to equal 1.5 times 10 equals 15 volts. And then I know that VAB equals the simplest way, which is where most circuits tend to work, equals E minus that. So it's 30 minus 15 equals 15 volts. Okay, so I've just proved, but if you can use the logic, you don't need to show those steps. You just go, right, same resistance, same PD. Okay, so we're trying to find out about the bulb brightness. Well, I know that those together are 30 ohms. I can ignore this bit down here. I know the bit with the bulb in is 30 ohms, and I know it's got 15 volts across it. Okay, so I'm going to work out the current through here. Okay, I should just say, let's make that a number, I2. So I2 is going to equal V over R again. It equals 15 volts now here, divided by 30. So it's just the current through that side. I'm not worried about this bit. So divided by 30. And again, I tend to put the units in just to help me. 0.5 amps. So if you're a genius, ignore that. If you're a genius, that's going to be 0.5 amps labelled up. You can straight away see, well, 1.5 went in, so this must be 1.0 amps. So if we do that, I know what the PD is here, because I know the current going through it, and I can ignore that bit now. So V of the bulb equals, let's put in the equation, IR, or I2R to be precise, that's going to equal 0.5 times 12 equals 6 volt. Final answer, the bulb's rated at 6. Is the bulb the normal brightness? Notice I went back and checked the question. Equals normal brightness. Excuse me, I can't spell. Normal brightness. Okay, so that is your answer. Lots of maths done it, but this one is actually quite long because you actually got to work out the total resistance for it. Okay, now to practice further, there are more questions which just have what is the resistance. Yeah, so again, 6 in parallel with 9, add on 4. You can do them all in one step. You can add those ones in step simply because they just add up. But if you want to do the resistance in one go, again, the advantage of using that technique is you can combine that into that. For example, 4 ohms plus, in brackets, 1 over 6 plus 1 over 9 to the minus 1. Okay, so you've got your parallel bit and you can then just put it all in one line. It does make it a lot easier to do. So 3/18, 2/18, so that's 5/18, 18 over 5 equals 4 plus 18 over 5. Okay, and if you put that in, then fairly straightforwardly, you've got 3 plus 3 remaining, so that's going to be 7.635, so 6/10 ohms. Okay, notice how simple, how neat you can do it. Okay, but yeah, practice resistor combinations, really common, but as we saw in questions 14 and 15, you're often actually just working on voltages and currents. Okay. Again, if you find having trouble thinking about complex circuits, you know, these two obviously they have to be in parallel because as the charge comes through it sees both options at the same time. So in this one, you're seeing that in parallel with that. Okay, so again, I would join them together so you can see what's going on. So it's an 8th plus a 24th reinverted at the end. Okay, so practice those. Going to just go back to the notes because sometimes you have some horrible looking circuits, but quite easy to do. This is a complex circuit, even though it's only a series circuit. But if we go down the route, it's nice and straightforward. So again, I'll get into the habit of Kirchhoff's second. It's going to be sum of the EMF equals sum of the PDs, okay, which I write as IR. Just makes it a little bit easier. So let us take, we'll go for the bigger one just to avoid the maths. So 14 minus 12. Notice that. So your 14 is pushing the current actually in the direction it says. That's okay. And so that's kind of going to come out of there. And you're fighting 12 that are trying to push it back. So I'm going to subtract the 12 from it. And because it's a nice simple circuit, I'll put the I and the R's separately. So I've got 1.8 plus 0.2 ohms. Okay, so what I've got is 2 equals I times 2. I equals 1.0. Notice I'm not doing one significant figure. Okay, so that's my current. That's all I need. Notice it's plus, which means that it's positive for the direction flowing from the 14 volt cell. Okay, so that's the one we took to be positive. So because our answer is positive, it fits with that one. Okay, if we'd done it the other way round, you'd just end up with -1. If we're taking the 12 to be the plus, so current flowing out. And because it's -1, it means we've got it in the wrong direction, it's going the opposite way. So it's still flowing in the same direction, and you can tell from your final values. So, any circuit, unless it's just resistances, okay, like the question I've just shown you, the bottom question I've just shown you, unless it's those, then go through the same loops. Okay, number one, where is the current flowing? That's always going to be the basis of what you want. Okay, and even if you've got a really large resistance, there'll always be some. Okay, so that is Kirchhoff's first. Okay, geniusly, they're not really my rules, which are the loops where PD is lost? Kirchhoff's second. Okay, and then from there draw on all values of I and V as you calculate them. Okay, and where we did it in class, you could see with question 14 and 15, especially for question 15, I just worked out the circuit, just labeling up the circuit leads you on to the next step, next step, next step, without even looking at the questions. Okay, so break down the circuit, what's going on, where is it, simplify it as much as you can as you're going on. And that is how to deal with all electric circuits.